In the previous chapters, we learned about electric fields as well as we learned about magnetic fields. Now, in this chapter, we're going to learn about the relation between those two fields, electric fields and magnetic field. Okay, now the first point I want to repeat again, a current carrying conductor always produces magnetic field. Okay, so now if you take a small conductor, when it is not connected to a source, what happened? There are thousands of millions of electrons. These electrons are randomly moving around this conductor, so there is no net displacement, so current passing through this wire is zero. Now when I connect it to a battery, a source, okay, so this negative plate has lots of electrons, so electrons are going to move in this direction. Electrons are going to start from the negative plate, reach to the positive plate. Now, but the conventional current, we always say current is flowing in this direction. Now, whenever you create a potential difference, what happens? There is electric field inside this conductor. That electric field is responsible to move these electrons. Okay. So from this, we know that current is moving, electron is moving inside the wire is because of the electric field. Now electric field is responsible to produce the magnetic field, because whenever electron is moving, we say that's a current flowing. So whenever current is flowing inside a wire, it produces magnetic field. Okay, so from this we know that electric field produces magnetic field. Okay, now when it comes to the electric field, now we want to find whether a magnetic field is going to produce electric field or not. Okay, now electric field always starts at a positive charge and ends at negative charge. So that's how electric field is created, right? So it always starts at positive charge, ends at negative charge. Okay. Now, so for example, if you take a capacitor, okay, parallel plate capacitor, there is always electric field between these two plates, assuming this distance is very small compared to the area of the plate. Okay, what is the value for the electric field? Formula for electric field: E equal to V over D, voltage over distance. V is the potential difference applied between those two plates. Okay, so a voltage creates electric field basically. Okay, that's what we learned from one of the previous chapters. So far we discussed two important points. One is a current carrying conductor produces magnetic field, and a current is nothing but flow of electrons. So electrons moves because of the electric field inside the conductor. Now we can say electric field is responsible to produce the magnetic field. Now, okay, now we'll find the other way, whether the magnetic field is going to produce the electric field or not. Now, what is Ampere's law? Ampere's law is nothing but a closed integral B times dl equal to mu naught times I enclosed. Okay. So magnetic field produced by current carrying conductor in a closed surface, or in a closed length. So here is a conductor. If I remember, there is the I current passing through it. So if you want to find magnetic field around this loop, okay, it's not a circle or a different shape or square. Okay, so the closed integral of this is dl. Closed integral of this dl is nothing but b mu naught times I enclosed. That will give you the magnetic field produced by that conductor. Now I'm going to take a small capacitor. Say I current is passing through this capacitor. I current is passing through this capacitor. So whenever there is a current passing through this capacitor, definitely there is electric field between these two. Now, one important thing, this current, is it a constant current or alternating current? If it is a constant current, it will start charging. Once it is fully charged, capacitor act like an open circuit, so there is no current passing through it. Okay, so I'm going to take this as alternating current, okay, instead of DC. So when it is alternating current, so current direction changes with respect to time. So this electric field direction is also changes with respect to time. Now I'm going to see what is the I'm going to see whether we can apply this um, Ampere's law. So here are two surfaces. Okay, here is a cup I'm taking. So here is surface A. Okay, here is surface A, and this is surface B. Surface B. Okay, so surface A, by using Ampere's law, I can tell there is I current is entering. So I can find the magnetic field produced by this current conductor. Now, how about here? There is electric field. Is there any current between these two plates? There is no conventional current, right? Because current comes here and then energy is going to transfer through these two plates via electric field. So between those two plates there is no current. So the current entering through the surface B, I would say 0. If current entering through the surface B is 0, can we say there is no magnetic field here? That is not true. Okay, so that's what the Maxwell found. So what he did, he modified the existing Ampere's law and he added one more term to find out the relation between the electric field and magnetic field. Okay, we know that charge on that conductor's Q equal to C times V, where V is the potential difference between those two plates. And we also know V equal to E times D. E is the electric field, D is the distance between the plates. D is distance between the plates. Okay, and so can I say Q equal to C times E times D, where C is the capacitance value. Okay, C is capacitance. If you remember capacitance, epsilon naught A over D. There is a K constant. That constant is dielectric material constant. I'm going to take it as 1, assuming it's filled with air. Okay, so can I say C? I'm going to substitute that epsilon naught A over D times E times D. So D get cancelled out. We'll end up with E times epsilon naught times C. That is the charge on each plate of the conductor. Each plate of this capacitor. As I mentioned, we have to choose this I as alternating current instead of direct current, because if I choose this as direct current, this current is going to be 0 in quick movement. Okay, once that capacitor is fully energized or fully charged. To charge a capacitor, it takes few milliseconds or maybe a second at the max. Okay, so that must be an AC current. So if I take di by dt, or sorry, I equal to, can I take this as I equal to dq by dt? So the current passing through this capacitor, as I said, I'm going to take that as alternating current. Alternating current, I can say dq over dt. So if I differentiate this, d epsilon naught A times E over dt. Epsilon naught is a constant. Area of the plate is also constant. It's not depending upon the time. So I can say I equal to epsilon naught A dE by dt. Actually, I'm going to keep the area inside. So d E A E A over dt. Epsilon naught is right there. Now, can I say E times A times cos theta as phi E? Phi E is the electric field. So I can say I equal to epsilon naught d phi E by dt. This I is nothing but the current. So the equivalent current inside this capacitor. So in between those plates. Okay, this I, we call this as displacement current. Okay, displacement current. So now if I use the Amperes law, B times dl equal to mu naught times I enclosed, right? So if you look at the second surface, in the second surface, what is the current? That current is nothing but this alternating current. Okay, so this I enclosed for surface A, I can take that as I. So mu naught times I plus the current in between the plates, I can take that as epsilon naught d phi E by dt. d phi E by dt. Okay, so from this, I can say this is called modified Amperes law. So mu naught I enclosed plus mu naught epsilon naught d phi E by dt. So this indicates that phi E is the rate of change of electric field, or its electric flux basically. So rate of change of electric flux produces the magnetic field. Okay, so from this we can say rate of change of magnetic field also produces electric field, or sorry, we already know rate of change of magnetic field produces electric field. So from this is modified Ampere's law. It's called Maxwell equation. There are 4 Maxwell equations. I'm going to talk about it in a second, but this is one of them. So from this we can tell rate of change of electric field produces magnetic field. So rate of change of electric field produces magnetic field. As I mentioned, there are 4 equations. I mean, Maxwell defined that these 4 equations give us the relation between the electric field and magnetic field. Okay, so the first one is Gauss's law. If you remember, closed integral of E times dA equal to Q enclosed over epsilon naught, Q enclosed over epsilon naught. So this is Gauss's law. So Gauss's law tells us that charged particles create electric field. So closed integral of E times dA equal to Q enclosed over epsilon naught. That's Gauss's law. So from this, a charged particle create electric field. This is basically Gauss's law, but he reiterated it because it is helpful to define the relation between the electric field and the magnetic field. Okay. This is the first one. Now the second one is closed integral of B times dA equal to 0. This is Gauss's law for magnetism. Gauss's law for magnetism. So this tells us that it is impossible to have a monomagnetic pole. Okay, so at this point I'm going to rewrite this. Okay, so this is modified Gauss's law, or sorry, Gauss's law for magnetism. There are no magnetic monopoles. That's what it tells us. This is the second law. Third one is, it's just a reiteration of Faraday's law. E times ds equal to minus d phi m by dt. Okay, so basically rate of change of magnetic field phi m, we know that induced EMF E equal to minus n times d phi by dt, where phi is the magnetic flux here. Okay, M is the magnetic, B is also magnetic because magnetic field is represented by B. So don't confuse. I always use B. Your textbook is using M, so that's the reason I'm using these two. But don't get confused. D phi B by dt. So induced EMF E equal to minus n times d phi by dt, and we know that E is nothing, I mean, this is the voltage, induced EMF. So basically this is nothing but voltage. Voltage is nothing but, can I write this as E times D, where E is the electric field, D is the distance. So closed integral of E times ds, d is the distance, I mean s is the distance, there is nothing but rate of change of magnetic field. So basically this is Faraday's law. According to Faraday's law, you can tell rate of change of magnetic field produces the electric field. Okay, and the fourth one is Maxwell's modified equation, or Ampere's law modified by Maxwell, which is B times ds equal to mu naught I enclosed. This is what Ampere's law. Now Maxwell included epsilon naught mu naught d phi by dt. So rate of change of electric field also produces the magnetic field. Okay, this is the fourth one. This is Ampere's Maxwell equation. Okay, so this tells us that rate of change of electric field produces the magnetic field, and from the Faraday's law, previous law, you can tell that rate of change of magnetic field produces the electric field. Okay, thank you. I'll continue about this chapter in the next video.